Hi बच्चों, this is lecture 6 of number theory and it's part 2 of HCF and LCM. I hope that you have seen the first part completely and there were some interesting properties at the last that I have discussed through. I'll continue from there. There are several properties that has to be added here. Actually HCF and LCM is so vast and it contains a lot of Olympiad questions here. So I need to discuss all the theories that I included. So first we'll start with the property. So what is the property? First is HCF and LCM of powers. So how do we find the HCF and LCM of powers? Now there is a simple property that relates HCF of a to the power n, b to the power n is actually HCF of a, b per power n. It means first find the HCF of a and b and then raised to power n is same as HCF of a to the power n and b to the power n. We will explain how. LCM again a to the power n comma b to the power n is equal to LCM of a comma b raised to power n. Now, so what does it mean overall? It means HCF slash LCM of or a and b raised to power n is same as finding HCF or LCM, first LCM of a comma b first and then raising it to power n and then raise it to power n. It's same but how? That is what we need to explain. Now if we go over to the proof why it happens and then we'll see the example to clarify the statement. Now for the proof part, let's say I will just take a single factor. Earlier also I have taken only a single prime factor. You are not required to prove with all the prime factors. If for one it is okay, so for every other prime factors it will be okay. So we can say let's a is equal to p to the power x into some other prime factors. Now other prime factors I am not taking into account. Okay. Now for b it will be p to the power y into some other prime factors. Now what is x? X is exponent of prime p in number a and what is y? Y is exponent of prime p in number b. Now what was RHS? I am talking of HCF. What was RHS? RHS was HCF a comma b raised to power n. So it means first find lowest of x and y which are the exponents and then that is what I am saying. It means find minimum of x comma y and then raise to and then raise HCF to power n. So it becomes n times, I am talking only of the exponent. Means, for example, if x is less than y, say, so what is the power of p that will come through? So it will be px. When I raise to n, so it will become p to the power nx. So I am talking of exponents. So it will be n into minimum of x comma y. Super. Now if we check LHS left hand side, so what is written? HCF of a to the power n comma p to the power n. Now what does a to the power n means? It means p to the power x into, there will be some other prime factors I am not interested in. So this will be p to the power nx. Again b to the power n will be p to the power y and goes on per power n. Now which will be p to the power ny into some other prime factors. For example, if it is 6 can be written as 2 into 3. I am only interested in 2 main. I am just talking of only one prime factors and we are seeing whether it is true for one prime factors, then it will be true for other prime factors as well. Now a to the power n is done, b to the power n is done. Therefore HCF a to the power n, b to the power n is equal to minimum of nx, ny. Let's say it will be nx, then we are done. So therefore LHS and RHS are equal. Okay. So I can give an example to clarify it further. For example, if I talk of minimum 3 into 2 or 3 into 5 is what? This implies minimum of 6 comma 15, which is equal to 6. If we talk 3 into minimum of 2 comma 5, so that is 3 into 2, which is again 6. So that is nx, ny is equal to n into minimum xy. That was the statement. Now similar case for the LCM. For LCM, same case for LCM. But here what we are required to take? Maximum value, max of x and y. And the procedure will remain same. Okay. Now suppose I take another example. Let's say for HCF, if we are taking some other value, say a is equal to 12, b is equal to 18, and choose n something as 3. Okay. Now what we are trying to check? HCF of 12 का cube comma 18 का cube is equal to HCF of 12 comma 18 का cube. That is what we are required to prove. Now how do we do it? So basically, let's see, for 12 it can be written as 4 into 3. For 18 it can be written as 3 ka square into 2. So HCF of 12 comma 18 is of course 6. I am just explaining so that you can understand. Minimum of 3 and 3 square, minimum of 2 square and 2. So this will be 6. 3 into 2, that is 6. Now therefore HCF of 12 comma 18 whole cube will be 216. True. Now what is 12 cube? 12 cube is 144 into 12, which is 1728. Now what is 18 cube? 18 cube is 5832. That I have already calculated before. So if we are trying to find HCF of 1728 comma 5832 and check out the prime factorization, instead of multiplying we could have also directly written, that is 2 square into 3 ka whole cube. So 2 to the power 6 into 3 cube comma 18 cube can be written as 2 ka cube into 3 per power 6. So if I choose the minimum of this 2 cube, so that is 2 cube into 3 to the power 3. So basically it will be 8 into 27, which is again 216, and this is proved. Same way for the LCM we can prove it. Okay, done. So let's say this as one of the property, and we will do next property. So next property of HCF and LCM says, if a number divides both B and C, then A must also divide the LCM of B and C. Now how do we do it? So for the solution part, it says, if a number divides both B and C, if a number, let's say A divides both B and C, then A must also divide the LCM of B and C. Of course, it's obviously true. If it is dividing B and C, then it obviously will divide LCM of B and C. Let's check out. what we are saying, according to question, A divides B and A divides C. What we are required to prove? We are required to prove A divides LCM of B comma C. That is what we are required to prove. Now, again, for every provence, there is a simple thing that I will do. What? I will consider any prime factor of A. Let's say, let's say, let's say a prime factor of A is P, and and exponent is K. It means there are K times that P is repeated. So therefore, this will be P to the power K. Now, if it is P to the power K, so then if A divides B, then P to the power K must also divide B. It means if, see how the conclusion will be, if A divides B, then at least the exponent of P in B is K. It can be more than K, but minimum it shall be K. Similarly, if if A divides C, then at least the exponent of P in C is K. This is true. Okay. Now, how do we find the LCM? LCM is chosen. How do we find LCM? LCM of B comma C. LCM of B comma C is chosen in such a way that what we do, we take the highest power of each prime factor in either B or C. So we choose highest prime factors in either A or B, directly in either A or B. Done. Now, it means for example, if I choose B and C, powers of P, so power of P will at least be K. Now, power of P will at least be K. Now start choosing at least be K. Now K, this P to the power K is in both. So it means every prime factor power in A, prime factor power in A must be or less than equal to power of LCM of B comma C. This is true. Therefore, A must divide. The logical conclusion is A must divide LCM of B comma C. Now it feels so intuitive. Of course, if A is dividing B and A is dividing C, so it must divide the LCM of B and C. Why? Because LCM of B and C, B will divide LCM of B and C. C will also divide LCM of B and C. Now you can stepwise understand that it is true, obviously, but proof requires this method. Okay, but what is the use of this? Amazing use. Let's say one example. I'll tell you, let xy belongs to integer such that 13 divides 3x plus 4y and 13 divides 2x plus 3y. Okay, now what we are required to prove that a simple question, but we need to understand why this property is important. Prove that 13 divides x and 13 divides y. Now how we are gonna do it? See, what we are required to do, from this point we have to reach only for x. So what can be done? I have to remove y. Matlab, when I need to prove 13 divides x, I need to remove y. I need to remove y, and when 13 divides y, I need to remove x. Done. Now let's say we can do one thing, that 3x plus 4y is multiplied 3 times. Why? Because 4 into 3 and 3 into 4, this will become 12. So I can say 13 divides 3 into 3x plus 4y. We have already done in divisibility. Again 13 will divide also 2x plus 3y into 4. This is true. Now, so therefore, this is equation 1. This is equation 2. By divisibility rule, we know that 13 must divide. If 13 divides A, we know this property. If 13 divides A, 13 divides B, then this implies 13 must divide A minus B. So basically 13 must divide here 9x minus 8x, and 12y gets cancelled. So 13 must divide x. Superb. Superb. Now similarly for second part, what we can do, we are required to eliminate x. So 13 divides 2 into 3x plus, what is there, 4, 2 into 3x plus 4y, 2 into 3x plus 4y, true. Why? If 13 divides 3x plus 4y, it is given, it will also divide the multiple of 3x plus 4y, true. Again 13 divides 2x plus 3y, so 13 will divide 3 into 2x plus 3y. So this is third, this is fourth. Now if I subtract 4, I'm sorry, this is 3, so I have to multiply with 2. Super. No, I need to eliminate what I have already proven for x, so this time I need to prove for y. So true, correct. Then I'll say कि subtract 4 minus 3 on right hand side. So 13 will divide 6x will get cancelled, 9 minus 8, that is y. 13 will divide y. Superb. Done. Next. Now next property says, again next property says what, if a number, suppose if a number d is there, d is a multiple of both b and c, then d is also a multiple of HCF of B and C, Again, this is very obvious but can be used in Olympiad proofs. Now for the solution part, so what we know till now, if a number d is a multiple of both b and c, then d is also a multiple of HCF of b comma c. Okay, done. So how do we proceed? If number d was there, is multiple of both b and c, then d is also a multiple of HCF of b and c. Of course, HCF of b and c, what does it mean? It is the highest common factor that divides b and c both. So this property is quite obvious, that of course d is multiple of b and c, then d is also a multiple of HCF of b and c. But how do we prove it? Let's say b, c, d belongs to z, integers. So if b divides d and c divides d, then what we are required to prove? Then HCF of b comma c divides d. That is what we are required to prove. So very straightforward in the sense, we know HCF of b comma c. What I said, actually I am going to prove the same way. We know HCF of b comma c will divide b, and we know that b divides d. So by transitive property, if you remember some transitive property says if x divides y and y divides z, then this clearly implies x divides z. So here HCF of b comma c divides b, and b divides d. So basically HCF B comma C divides D, and same is true for the second part. Understood? Now next, say there is what is the application of this? What is the application of this property? So application, actually it has amazing application. Um, what Where does it come from actually? This if a number D is a multiple of both B and C, then D is also a multiple of HCF B comma C. Actually it comes from somewhere that has a broader version and is widely used. It means we say a number D is a multiple, actually this is the correct statement completely, is a multiple of B and C, B and C, if and only if and only if it is a multiple of their LCM, it is a multiple of their LCM. So basically instead of saying application, I can directly state that this something looks like fundamental LCM principle. Fundamental LCM principle. I can directly say fundamental LCM principle instead of saying that yeah there are certain applications. I can directly say yeah this is one of the thing that we need to know. The way like for it exists for HCF, the same way it exists for LCM. Okay, so this is known as the fundamental LCM principle. Um, where to use this? Actually, in future courses will solve system of congruences, and we will also solve Chinese remainder theorem using this Chinese remainder theorem. We will also solve that Chinese remainder theorem. Done. Let's say one of the example. Now an example, say find the smallest positive integer n that leaves a remainder of 2, that leaves a remainder of 2 when divided by 7, and a remainder of 4, when divided by 9. Now how would we do this? When divided by 9, what's the procedure? Question says find the smallest positive integer n that leaves a remainder of 2 when divided by 7 and a remainder of 4 when divided by 9. How do we formalize the statement? Let's say it be n, because it is already written n, so n is congruent. Now how do we write this? N is congruent. I have already told you a bit about congruence while I was discussing permutation and combination. So how it is read? N is congruent to 2 modulo 7. It means simply 7 divides n minus 2. Done. Now again n is congruent to 4 modulo 9. What does this statement means? Simple. It means 9 divides n minus 4. Done. These two things are given, that it leaves remainder 2 when divided by 7 and remainder of 4 when divided by 9. These two are things are given. Now how would we do? Say here 7 divides n minus 2 and this is n minus 4. Now what is the way out? If you can check, this difference of 7 and 2 is 5 again, and this difference of 9 and 4 is 5 again. So what is the smart strategy that we are going to do? That number 5 is always coming here for both the cases when I am subtracting. So it means n minus 2 is a multiple of 7, what I can do is a multiple of 7. So I add 7 on this side. This can be done. While in congruence modulo, I can directly do here. N minus 2 plus 7 can be done. So 7 divides n plus 5. 7 will divide n plus 5. Similarly, 9 will divide n plus 5. Why? I added 9 to n minus 4. So n minus 2 is multiple of 7. So n minus 2 plus 7 is also a multiple of 7. Is also a multiple of 7. Why? Adding 7 doesn't change the multiplicity. Okay. Similarly for the second part. Now, so I can write here n minus 4 is a multiple of 9. So n minus 4 plus 9 is a multiple of 9. Superb. Superb. It means, what is the final conclusion here? Sorry. Final conclusion says 7 divides n plus 5 and 9 divides n plus 5. It means, now check out what was written here. A number D is a multiple of B and C if and only if it is a multiple of the LCM. It means n plus 5 is common multiple of 7 and 9. Common multiple of 7 and 9. How is this possible? How is this possible? It means what does this imply? N plus 5 is also multiple of their LCM. Multiple of their LCM. Now again, how is this possible? Simply n plus 5 common multiple of 7 and 9. So n plus 5 is also a multiple of their LCM, that is 63. So I can say strictly that 63 also divides n plus 5. Why this? You see the statement here. What was written? A number D is a multiple of B and C if and only if it is a multiple of their LCM. So since n plus 5 was multiple of 7 and 9 both, so n plus 5 must be a multiple of their LCM also, that is 63. So we can say that 63 divides n plus 5. Superb. Now what we are looking for? We are looking. So how does this look like? This statement means n plus 5 must be equal to 63k for k belonging to integer, that is z plus. Actually it can belong to z minus also, but here we will be considering positive integers. So n will be equal to 63k minus of 5. So 63k minus 5 means, it means we needed what? We needed the smallest positive integer n. So how do we find the smallest positive integer? Put k is equal to 1. Put k is equal to 1. Then n will be equal to what? 63 into 1 minus 5, that is equal to 58. So what was the question? Find the smallest positive integer n that leaves a remainder of 2 when divided by 7 and remainder of 4 when divided by 9. Let's check out. So if I divide 58 by 7, so 7 8 56 2. If I divide by 9, the remainder is 4. Okay. But you will say, sir, choose k2. So obviously what is going to happen? So this will become 121, which is greater than 58. Hence the smallest positive value will be 58. Superb. A nice thinking problem where you can pause and think for some time and then see the solution. Okay. Now again, let's say there is another question. Question is the sum of two positive integers. Okay, positive integers a and b is 360. Okay, the LCM A comma B is 20 times HCF A comma B. Find A and B. Find A and B. Now how do we do it? What's the idea? First of all the thing, if I consider HCF of A comma B, let's say this as X, then what will be LCM? LCM of A comma B will be 20 times HCF, that is 20x. Now it's very easy. Why? We know one of the property that LCM into HCF is equal to A into B. So what is LCM into HCF? 20x square, and that is equal to A into B. Now this is one equation. This is equation number 1. But how do we find the other value? Now we know the sum of two positive integers A and B is 360. Will this guide something? Yeah. We know HCF that is equal to X is largest number that divides both A and B. Divides both A and B. So basically in this case, what we are gonna say, A will be equal to h of x and B will be equal to h, say h of x and B will be equal to what? Since x is there, h x, yeah, and B is equal to x h ix. After h we can say it is ix because HCF is taken as x. Or instead we can do one thing. It's correct. Let it be. So A is equal to h of x and B is equal to I of x. Now what we need to do? We need to do one thing. Can we substitute it here back and first? So what will happen to the first equation? 20x square will be equal to AB, that is h of x into I of x, that is equal to 20x square will be equal to hi x square. Hence x square will get cancelled. So product h or into I will be remaining as 20. Now again, according to the question, it is given the sum of two positive integers A and B is 360. It means according to question, A plus B is given as 360. Now what is A? A is written as h of x, hx plus B is written as I of x, and that is equal to 360. So therefore, if I take x common, h plus I is equal to 360. Now, how do we find the value? Again, this is important. We know that hi is equal to 20. That is given. Now, please remember another thing, that HCF of h comma I must be equal to 1. Why? They must be co-prime. They must be co-prime. Okay. Why? Because I have already taken highest common factor out. Now, how do we check? First, we can check h comma I as 1 comma 20. 1 comma 20. Now, therefore, h plus I will be 21. But 360 by 21 is not an integer, so not an answer. Again, h comma I can be equal to 4 comma 5. If I take 4 comma 5, then h plus I will be equal to 9, and therefore x will be equal to 360 by 9, which is equal to 40. This can be the answer. This can be one of the answer. So next, anything else that can be done? No, 10 into 2, they are not co-prime. So these are the only two possible options. Superb. It means we have got our value of x, and that is equal to what? That is HCF. HCF is equal to x is equal to 40. And what else we got? We got the value of h comma I. So h, say h can be, uh, let's take 4 and I can be 5. So therefore the numbers are what we were required to do. We were required to find out a and b. So therefore a will be h of x, that is 160, and b will be h of y, that is 200. Or we can say that can be exchanged, or vice versa. Vice versa. So basically the integers are 160 and 200. So 160 and 200, these are the integers done. Next. Next. Next question says, find number of positive integers n. Now slowly and gradually the level of questions will rise, for which HCF n square plus 6n plus 10 comma n plus 5 is greater than 1. It means HCF is greater than 1 for these two values. So we need to find the number of positive integers n for which n square plus 6n plus 10 comma n plus 5 is greater than 1. It means they are not coprime. They are not coprime. So that is the meaning of it. Now how do we do it? So basically HCF of, now here we are required to use the property. So we know the property that HCF of a comma b can also be stated as HCF of a comma b minus some, we can say that b minus some c dot a, or we can say some k by c dot a, we can say like this. It means for any integer k, for all k belonging to z. It means we can multiply. What does it mean? We remember HCF of a comma b is also equal to HCF of a comma a plus b, or a plus p by q into r. HCF of not r, it can be b. This property I have already made you write in the previous lecture. So HCF a comma b can also be written as HCF of a comma b minus a. Again, any k by c times of a, or even if you want to remove c, that is b minus k times of a. Okay, so what is our objective? Eliminate n square. Our objective is to eliminate n square. So how do we eliminate n square? So the best way to do this is HCF n square plus 6n plus 10 comma n plus 5 can be written as HCF n square plus 6n plus 10 minus of n into n plus 5 comma n plus 5. Done. So how do we proceed then? HCF of n square plus 6n, n square gets cancelled, 6n plus 10 minus 5n. So this is n plus 10 comma n plus 5. Superb. Now HCF of n plus 10 comma n plus 5 can further be reduced. How it can be reduced? Again with the same property, that can also be written as HCF of n plus 10 comma n plus 5. So this is equal to n plus 10 minus n minus 5. Why? I have already stated and proved the property that HCF of a comma b can be written as HCF of a minus b comma b. Okay? So this is true. Now, so therefore n plus 10 minus n minus 5, that is 5 comma n plus 5. Now what next? We got till here. Now we can't subtract further. So basically what does it state? That HCF of 5 and any other integer which is n plus 5 here, n plus 5 must be a divisor of 5, must be a divisor of 5 at least, divisor of 5. It can be divisor of 15, it can be divisor of whatever, but at least this must be the case. Now what are the divisors of 5? The divisors of 5 are 1 and 5, but they are saying in the question that HCF must be greater than 1. So if HCF is greater than 1, which case are we required to take? So it means the HCF greater than 1, the only possible value will be what? HCF is equal to 5. So it means we can say HCF will be 5 if and only if n plus 5 is a multiple of 5, is a multiple of 5. Of course, unless and until they are multiple of 5, they will be co-prime to each other. If they are co-prime to each other, the HCF will be 1, which will contradict the statement of the question. So therefore HCF is greater than 1, and hence if n plus 5 is a multiple of 5, then it can be written as 5, 10, 15, 20, and it goes on. And there are infinite values. There are infinite values of it. Okay? Next question. Now, next question, again a bit standard one, says for a positive integer n, for a positive integer n, let h of n be defined as h of n is equal to HCF of n comma 42. Find sum of all positive integers, all positive integers less than all positive integers n less than 100 that satisfy the equation. Which equation will they satisfy? H n का whole square minus 8 h n plus 12, that is equal to 0. Now this is the condition. So for this question, quadratic has been combined with question of HCF. Now how do we proceed? So see here, let Hn be defined as Hn is equal to HCF of n comma 42. Now again this is given as quadratic in Hn. So we can do one thing. For solution, let's solve this quadratic first. So let h of n can be considered as some h. Then this equation becomes h square minus 8h plus 12 is equal to 0, where if you middle term factorize it, then it will be h square minus 2h minus 6h plus 12 is equal to 0, again which implies h minus 2 or h minus 6 is equal to 0, which implies h is equal to 2 comma 6. It means therefore HCF h of n shall be equal to 2 or 6, either 2. But what they are saying again, now this is HCF, but HCF n shall be less than 100. Now there is a case we need, what do we need? We need all you can say x that belongs to z plus a positive integers and is less than 100, where HCF of n comma 42 is equal to 2, that is written, or HCF of n comma 42 is 6. Now these are the cases that we need to consider. So case 1. So in case 1, let's say HCF of n comma 42 say is 2. Now it means if HCF of n comma 42 is 2, there are 2 or 3 conditions that must be required. N must be multiple of 2, true, but now what is the prime factorization of 42? 42 is 7 into 6, that is 2 into 3 into 7. So it n must be a multiple of 2 but not of 3 and 7, not of 3 and 7. Why? If there were to be any factors of 7 or 3 in n, then the HCF would not be 2, it would be greater than 2. Understood? It means what we are looking for, we are looking for multiples of 2 that are less than 100 but not multiples of 3 and 7. It means it means that first we need to find even numbers less than 100, even numbers n less than 100, and subtracting those that are multiples of that is but not of 3 and 7. So if but and subtracting those of, now if 3 is combined with 2, see what do we need? We need all even numbers. It means 2 must be there for everyone. Now for one time let it be 3. So subtracting those of 3 into 2, that is 6 multiples of 6. I am talking of multiples of 6, and those of 14. Why 14? Here it is 7, here it is 2, so multiples of 14. Now how do we count? We can count systematically. For example, even numbers. How many even numbers will be there? 2, 4, less than 100, that is 98. So what is the total number? 49 numbers. 49 even numbers first. Now with this 49 even numbers, what we are required to do? We are required to find the sum of all positive integers. Okay. So what is the sum of this even number? Sum will be, how to add it? How to add? We say there is an AP. So how many numbers? 49 by 2. First term plus last term. 98 plus 2, that is 100. So this will be 5, which is equivalent to 49 into 50, that is 2450. Superb. Now multiples of 6 less than 100. Let's start from 6, then go to 12, then go till 96, 16, 6, 96. So what is the total value? First tell me how many numbers would be there. Will it be 16 or 17? Think of it. It will be 16 itself, na? 6 into 16 is 96. So 16 by 2, first term plus last term, that is 102. So this will be 8 and 816. Next, multiples of 14, which is less than 100. So what are they? First is 14 and last is 98. How many are there? 7. So 7 by 2, 98 plus 14, that is 112. So what is the answer? This is 56, 76, 42, 75, 35, 392. So this is 392. But if we are subtracting this multiple of 6 and 14, what we are required to do? We are required to check also multiples of, if there is a subtraction sign, it means pi principle is being applied. So for applying pi principle, what we are required to do? First we are required to check what were the even numbers restricted. Now we are required to check multiple of 6, multiple of 14. But in this two case, there will be some extra counting. Why? Because some of the questions will have 16 and 14 both as common factor. So we need to subtract those numbers. So multiples of LCM of 6 comma 14. So what is the LCM of 6 comma 14? So it will be 42. So this will be 42. So 42 and that is less than 100, true? Now, so therefore, in this case, what are the values? What are the values? So in this case, sum will be 42 and 42 ka multiple, that is 84. So total will be 126. So again, therefore, apply pi. If you haven't studied pi, bachon, you see my videos on pi. It has been detailed exclusively so that you can cover all the aspects of the questions till IOQM. So here it is pi. Again, the sum of the numbers will be what? Sum of multiples of 6, sum of 6, sum of 14, sum of 14 and minus sum of 42, sum of multiples of 42, and we are done. Sum of multiples of 42. So this will be what? Total was 816. So this was 816 plus 392 and there is 392 and there is minus 126. So what is the value? So 896 and 392. So 292 and this is 256 and 82, 82,000 and 10. This was 12,6,826 and this was 166. Okay, if I subtract 166 from 816, so this will be 50 and sorry, I need to add up. So 8, 9 and this is 266. I'm sorry. So this will be 66, 76, 82. So answer is 1082 for this one. But overall answer will be what? We have calculated the total even numbers. What was the sum of even numbers? 2450. But what do we need? We need those numbers. Sum of all positive integers that satisfy this equation. Okay. So basically here it will be कितना 2450 total आया था and here it is 1082. So sum for case 1 will be what? 2450 minus 1082. What is the value? It's 10 में 2 8 again 4 8 6 and then 3 1368. So 1368 is the case for this when HCF is 2. यहाँ पे क्या आया था बच्चों? सम 6 टोटल केस 1 क्या था? केस 1 N और 42, HCF 2 था. अच्छा, अभी सेकेंड केस बाकी है, केस 2. केस 2 में क्या होना चाहिए? केस 2 में ऐसा होना चाहिए कि HCF कितना होना चाहिए? 6 होना चाहिए. सो HCF N, 42 शैल बी 6. अब 6 के लिए प्राइम फैक्टराइजेशन क्या हो जाएगा? 42 के लिए that is 2 into 3 into 7. Now what's going to happen? What we need 6 HCF. So it means integer must be multiple of 6, but not of 7. Must be multiples of 6 but not of 7. Multiple, not multiples. So multiple of 6 but not of 7. Now how to find this out? So actually we are looking for multiples of 6 that are less than 100. So we start 6, 12, 18 and this goes on till 96. But what do we exclude? We want a multiple of 7 but not of we want multiple of 6 but not of 7. So how do we omit? So 7 wale whatever the multiples are there, that is 7 into 6, 42. So how many multiples would be there? One will be 42, another will be 84. Nothing else. We have to exclude these two. So in total, if we start adding, so we say this will be 6, 12, 18, 24, 30, 36, 48, 54, 60, 66, 72, 78, now no 84, this will be 90 and plus 96. So if you start summing it out, 12, 18, 36, 36 and 60, 90, 126, 126, 130, 180, 180 plus 48, 228, 288, 294, 294, 354, 354 and 96. So 354 and 96. So this will be 450, 450 plus 72, 78 and 90. 4. So overall 72, 78 is 150, 240. Okay. So this will be 690. So this is 690. Now, so these are the total cases. Case 1, case 2, where n HCF n comma 42 is 6 and where HCF n comma 42 is 2. So these are the two cases. So for the first case, how many, what was the total sum? 1082. For the second case, what is the total sum? 690. So overall, what will be the value? So total sum is equal to 690 plus 10 sorry, 1368. So this is 1368. So basically what is the value? 8, 9, 6, 15, 6, 9, 10, 2058. 2058 is the answer. Now next question says, next question, the highest common factor, that is the HCF of two positive integers, that is a, b belonging to z plus, is 8. Is 8. Okay. And their LCM is 224, 224. How many ordered pairs? How many ordered pairs A comma B satisfy these conditions? Satisfy these conditions. So what is the way? Now, what is given? HCF is given, LCM is given. They are asking for the ordered pairs. So how to find it out? Now, for the solution part, first let us write what is given. HCF of A comma B is given as 8. And what is LCM of A comma B is given? LCM of A comma B is given as 224. 224 can be written as 224, 2, 112, 256, 228, 2, 14, 2, 7. It means 2 to the power 5 into 2 to the power 5 is 32 into 7. I am sorry. 2 to the power 5 into 7. Now, so LCM is given, HCF is given. That is, this is 2 cube. 2 cube. Now, what do we need to do? We need to find ordered pairs satisfying these conditions. So, which we have to utilize the method where we can with only these two conditions we will be able to find the ordered pairs. So basically what we need to do, let a is equal to 2 to the power x1 into 7 to the power y1. Why only these two? Because HCF and LCM consist only of 2 and 7, and b is equal to 2 to the power x2 into 7 to the power y2. Now HCF A comma B uses minimum exponent for each prime, minimum exponent for each prime, and LCM A comma B chooses maximum exponent for each prime, Now how to do? So one takes maximum, another takes minimum. So now these are the only possible exponents. So what we can do, minimum of, according to question, minimum of x1 comma x2, I am only talking of exponent, that is equal to 3. Now maximum of x1 comma x2, that is what? So maximum x1 comma x2 will be, it's written here 2 to the power 5. So this is 5. Now this comes from HCF and this comes from LCM. So it means one of the exponent must be 3. Why? Because HCF is 3. So if I am talking of minimum of x1 comma x2 is equal to 3, it means that one of the exponent need to be 3. If one of the exponent is 3, the other needs to be 5. So it means what we can say, x1 is equal to 3, x2 is equal to 5, but some will be saying that sir, x2 can be 3, x1 can be 5. So both of the cases can be there, and this is the case for x1 x2. Similarly for and we discussed about prime factor 2. We discussed here about prime factor 2. What about prime factor 7? So for prime factor 7, we can do prime factor 7. We can do one thing. Here it is y1 and y2, and for 7 there is only LCM which is coming as 7. So what we can do, minimum of, we can say minimum of y1 y2 will be 0. Why? Because 7 to the power 0 is equal to 1 is in HCF, and it can be maximum of y1 y2 which is equal to 1. Why? Because again 7 to the power 1 is in the LCM. So I am talking only of the exponents. So what are the possibilities of y1 y2? Either it is 1 0 or 0 comma 1. Done. Now we need to count the pairs. Counting the pairs. So how do we count the pairs? Say total cases. Now we have total cases, which is total number of pairs. Two choices for 2, two choices for exponents of 2, and two choices for exponent of 7. So basically we say two choice for exponents of 2 into two choices for exponents of 7. So basically there are 4 choices. So total number of pairs will be 2 into 2, that is 4. So what are the pairs? The pairs will be like this: x1 y1, x1 y1 again x1 y1, and x1 y1. So what are the pairs? We are talking of the LCM. How many ordered pairs satisfy this condition, and what we have considered? X1 y1 and x2 y2 pairs for A and B. So here is for A. This is for A. So what can be A? One can be 3 x1, and what is y1? Y1 can be 0 or 1. Okay. So x1 y1, either the pair can be 3 0, either can be pair 3 1. Okay. Similarly for x1 y1 there can be another thing. This can be 5 and 0, and 5 and 1. Similarly for x2 y2, we can have similar case. Again this can be, now we are talking of again x2 y2, we are talking of x2 y2 again, and we are talking of x2 y2 again. So what are the possible cases for x2 y2? Now when x1 y1 is 3 comma 0, so x2, what about x2? X2 can be either 5 or 3 and 0 or 1. So basically it can be 5 comma 1, it can be 5 comma 0, again it can be 3 comma 1, again it can be 3 comma 0. So these are the possible pairs. So can we say what are the possible values of A and B? Amazing, amazing. If we got to know what was A was 2 per power x1, 2 per power y1. Sorry, A was 2 per power x1 into 7 per power y1. So A is equal to 2 per power x1, 7 per power y1, and this B is equal to 2 per power x2, 7 per power y2. Okay, so basically what happens with A? This becomes 8, 2 cube, that is 70. So this becomes 8. And what about B? B becomes 2 to the power 5, 32. 32 into 7, that is equal to 224. Super. What about another one? This becomes 2 ka cube, 8 into 7, that is 56. And here it becomes 2 to the power 5, 32. Super. Again for this one, 2 to the power 5, that is 32 into 7 to the power 0, that is 32 into 1, 32. Again 2 ka cube, 8 into 7, that is 56. Super. So here 2 to the power 5 into 7. So this will become 224. And again this will become 224. Here it will be 8. This interchanges. So these are the total number of 4 pairs. Amazing, amazing. Now this brings to an end of the second part. In the third part, we'll do some good questions, maybe 4 or 5, and that will bring end to the concept of HCF and LCM. Thank you.